So in the last lecture, we talked a little bit about what the atmosphere is made of, what the atmosphere is. We talked about ozone and greenhouse gases. Well, for this lecture, we're going to talk more about the structure of the atmosphere, specifically the different layers of the atmosphere. We're also going to talk about air pressure and density, how they vary in the atmosphere, and so that's what we're going to be talking about today. Now, the goals for today, first we're going to talk about each of the layers of the atmosphere, similar to how we split our solid up into different layers, crust, mantle, outer core, inner core. Well, we can do the same thing with our atmosphere, and we can split it up into different layers. And we're also going to talk about what distinguishes one layer from another, and then also talk about where one layer ends and another layer begins. So let's do this. So, just a review from the last lecture. The atmosphere is held in place by gravity. And as a result, most of the atmosphere's molecules hang out near the surface. In fact, even though the atmosphere is hundreds of miles thick, 99% of the atmosphere's air molecules are only present within the first 30 kilometers, or approximately 19-20 miles. And in fact, even more are located even closer to the surface. So with that said, most of the air is down near the surface. And this creates what's called high density. Because most of the air molecules crowd the surface, the air near the ground has a lot of air molecules in it. And so you have a large mass of air occupying a relatively small space. However, as you rise in the atmosphere, you're going to have fewer and fewer air molecules in that same space. Let me give an example of this. So think about the room you're sitting in right now as you're watching this video. Well, the density in that room can be defined by the number of air molecules in it. So think about this. Right now, the room that you're sitting in has trillions and trillions and trillions of air molecules. Well, as you rise up in the atmosphere, you would have fewer and fewer air molecules in the same room, in that same space. Such as in the stratosphere, you may only have billions and billions of air molecules. In the mesosphere, it may be just thousands and thousands. And up near the top of the atmosphere, you may only have one air molecule in the entire room. And so air density decreases rapidly with height. The other thing that I really want to talk about when talking about air molecules in the atmosphere is that air molecules have mass. Every air molecule has mass, and as a result, it has weight. Don't believe me? Take a balloon, put it on a scale, measure its weight, then blow into the balloon, and then measure its weight again. And you will actually notice an increase in the overall weight of the balloon. You know, when you blow air into it. This is because air has weight. Well, air pressure is defined as this weight. So think about this. You're sitting in a room right now, and between you and the top of the atmosphere, there's several hundred miles between you and the very top of the atmosphere. And between you and the top of the atmosphere, there's all these air molecules. Well, those air molecules are weighing down on you. And that weight that you experience is air pressure. So first, talking about density, air density decreases with height. You have a lot of air crowding a small space near the surface, a lot less air crowding the same space near the top. But more importantly, let's talk about this air pressure more in depth. So, again, air pressure is the weight of the air above you. As a result, the higher up you go, the fewer air molecules you have above you. As a result, air pressure always, always, always decreases as you rise in the atmosphere. I assume if you're taking this class, you live in the Silicon Valley area. There's a road that goes from here over the mountains to Santa Cruz called California 17. And if you ever go up and over that highway, you will actually feel your ears pop. Well, the popping of your ears is your body's response to air pressure changes. And it's because air pressure decreases as you rise in the atmosphere. Surface air pressure is approximately 1,013.25 millibars. This is a number that I want you to remember. This number is very crucial, and we're going to use it a lot in this class. But what this actually means in terms of numbers that we're used to, 14.7 pounds per square inch. So think about if you took your thumb and your index finger and you made a circle by connecting the two. That circle is approximately a square inch. Well, right now, if you're at the surface of the Earth, if you're at sea level, you have 14.7 pounds of air weighing down on that 1 square inch of your body. So thankfully, we're used to pressure. Thankfully, our bodies are acclimated to it. But it does have major implications. And because our bodies are acclimated to it, going someplace with either higher or lower air pressure can actually have consequences. As you rise in the atmosphere, you'll always have less air above you. Why? Because you're closer to the top of the atmosphere. Therefore, air pressure always decreases with height. And it decreases exponentially. What that means is when you're near the surface of the Earth, almost all the air molecules crowd near the surface of the Earth. Well, as you get even a little bit higher, most of the atmosphere's air molecules are beneath you. So that results in a substantial decrease in the weight above you. So going up even a short distance, even a few thousand feet, not really that much, can result in a drop in air pressure of 10 to 20%, just with a little jog up a few thousand feet. So that's what an exponential decrease is. If we were to graph it, it would look something like this. Near the surface of the Earth, air pressure is 1,013.25. A lot of times we just say 1,000. I'll never give you a question on a test where you have to say 1,000 or 1,013.25. But what you'll notice is going up even a slight bit. So this y-axis here is altitude. Going up even a slight bit, just climbing just a little bit up this mountain, up Mount Everest, and you can experience as much as a 20 to 30% drop, a 200 to 300 millibar drop in air pressure just by going up a relatively short distance. So it's a big deal. So air pressure decreases with height. Now, one thing that doesn't decrease with height, ironically, is temperature. Temperature does some weird things with height. And this is how we layer our atmosphere. So the atmosphere is split up into 5 main layers, depending on how temperature changes in each layer. Well, the fact is, we're only going to worry about the first 4 layers of the atmosphere, because the 5th layer is very convoluted. But let's talk about these first 4 layers. The first 4 layers are the troposphere, the stratosphere, the mesosphere, and the thermosphere. The troposphere makes up 0 to 11 kilometers. That's approximately the first 8 miles of the atmosphere. The stratosphere goes from 11 to 50 kilometers, the mesosphere from 50 to 85, the thermosphere from 85 to 500, so now this is closer to 300 miles above the surface of the Earth. And then the exosphere is everything above that. I usually tell people the exosphere is essentially outer space. So we don't really worry about that. I want you to focus on these 4 right here. Troposphere, stratosphere, mesosphere, thermosphere. And in that order. So troposphere is the lowest, stratosphere is the next one, mesosphere is the next one, thermosphere is the last one. All right? So the boundary between any of these two layers is what's called a pause. So the boundary between the troposphere and the stratosphere is what we call the tropopause. It's the top of the troposphere. The boundary between the stratosphere and the mesosphere is called the stratopause. The boundary between the mesosphere and the thermosphere is the mesopause. And overall, our atmosphere looks something like this. Now, one of the things that you'll notice is that temperature, that's this red line here, kind of zigzags as you go up in height. What does this actually mean? Well, temperature changes with height differently in different layers. Here in the troposphere, and we're usually pretty used to this, temperature cools with height. This is why we see snow on the mountains but not snow on the ground. Because as you go up in height, temperature typically cools. However, as you rise into the stratosphere, temperature levels off, stops decreasing, and it begins to increase. And then the same thing happens once you hit the stratopause, the top of the stratosphere, temperature levels off again. Then as you enter the mesosphere, temperature declines again, and then levels off, and then you hit the thermosphere, and temperature increases again. So let's talk about each of these layers. The temperature levels off at the top of each pause. So at the top of each of these layers, you'll see a leveling off in temperature. Let's talk about each of these layers. First off, the troposphere. Unless you've been on a high altitude plane or have gone to outer space, you will spend 100% of your life in the troposphere. The troposphere is important because that's where our weather is. Substantial mixing occurs in this layer. And this happens due to temperature imbalances, which leads to pressure imbalances. We'll talk more about that when we talk about dynamics, but this is where all of this happens, all of this mixing happens, all of this turbulence happens. And so this is where our weather occurs. It occurs in the troposphere. In the troposphere, temperature usually decreases with height. Now there is one exception to this, and be very mindful of this exception throughout the remainder of the course. That one exception is near the surface of the Earth. Near the surface of the Earth, you have a very hot ground. And that hot ground heats up the air right above it, and that warm air rises. As a result, as this warm air rises, it actually heats up the air slightly above it. And so this creates a layer of warmer air near the surface, which causes an increase in temperature with height. This is called an inversion. Now, different locations are more prone to inversions than other locations. Many urban regions see inversions very regularly. And then there's also upper atmospheric conditions that can impact inversions. But inversions are very common near the surface of the Earth. Here you see an increase in temperature with height. However, in the troposphere, this only happens near the surface. Once you get a few thousand meters above the surface, you enter what's called the free atmosphere. And in the free atmosphere, temperature declines with height until you get into the stratosphere. We can actually take a look at the temperature in the troposphere using a weather balloon launch. So we talked about weather balloons a few lectures back, and I talked a little bit about why we launch them. And the key reason why we launch weather balloons is because they can give us an idea of how temperature is changing with height. We can then take that data and plot it on a plot called a Stuve diagram. For this week's exercise, for this week's activity, you're going to learn more about Stuve diagrams. But let me tell you a little bit about them here. This black line on the right represents air temperature. This black line on the left represents dew point temperature. We'll talk more about that later. But let's just talk about air temperature for now. Near the surface of the Earth, as you begin to rise up in the atmosphere, as you start all the way down here, this is the surface of the Earth, as you begin to rise in the atmosphere, you actually notice an increase in temperatures. This increase, this area here where temperature's increasing, this is your surface inversion. But then you notice as soon as we get a little above the surface, temperatures begin to decline. And they continue to decline all the way up to the top of the troposphere. And then up here you see what's called the tropopause. The tropopause, you then see another inversion. Here, air temperature levels off, and then it begins to increase. Now don't worry up here if you see another decrease again. Usually that will happen, but you'll definitely see an end of the cooling and a beginning of the warming. That represents the top of the troposphere. Now, how can you distinguish a surface inversion from a tropopause? Well, you can simply look at where the inversion is occurring. If the inversion is occurring down here, near the surface, that's your surface inversion. If it's occurring higher up on your plot, like it is over here, that's your tropopause. Now, once you get above the troposphere, something interesting begins to happen. Air temperature stops decreasing and starts increasing. At this point, you have entered the stratosphere. The stratosphere is the second layer in the atmosphere, and it contains Earth's ozone layer. Now, as Earth's ozone layer absorbs sunlight, it heats up. This is why the stratosphere warms with height, because it's heating up. And as a result, temperature increases with height. Now, this actually provides an interesting characteristic, in that this increase with temperature creates a cap, almost like the cap on a soda or the lid on a container, preventing anything from the troposphere from rising. This is why all of our weather and everything is trapped in the troposphere, because the higher temperatures in the stratosphere prevent air from rising up there. Air only rises when it's colder than its surroundings. Well, if the temperature up there is warm, air can't rise any further. We'll talk more about that later when we talk about what's called stability. Now, if you actually were to be up in the stratosphere and you were to look outside, it would feel like space. And a good example of this was in 2013, a gentleman named Felix Baumgartner actually went up to the stratosphere. He sat in a capsule that was tethered to this gigantic balloon, went up to an elevation of over 100,000 feet, and free fell all the way back down to the surface. If you haven't seen the video yet, it is awesome. The whole thing was sponsored by Red Bull, and it's just a really cool thing. But looking at the outside from that capsule, you can see the curvature of the Earth. So no, the Earth is not flat. You can see the curvature of the Earth, and it looks like outer space. And this is because the air up there is so thin. The ozone layer, and I mentioned it briefly in the previous lecture, the ozone layer is really important, and it takes place in the stratosphere. So the stratosphere is where our ozone layer is. Now, going above the stratosphere, we enter what's called the mesosphere. Other than what I'm going to talk about today, we won't talk about the mesosphere in this class. The mesosphere is the third layer of the atmosphere. Here, we've left the nice heating of the ozone, and therefore we've left this area where temperatures are increasing, and we actually resume a decline in temperature with height. As a matter of fact, temperatures in the mesosphere represent the coldest temperatures on Earth. The coldest temperatures in the atmosphere. Temperatures in the mesosphere can drop as low as negative 90 degrees Celsius. That's cold. Another interesting thing about the mesosphere, though, is that even though the air there is really thin, it's actually thick enough that meteors that begin to enter the atmosphere begin to feel friction and they begin to feel drag. And so they begin to burn up. So meteors actually burn up in the mesosphere. And then finally, as you get above the mesosphere, which is the coldest layer in the atmosphere, ironically, you enter the warmest layer of the atmosphere. This is referred to as the thermosphere. Here's why this layer is so warm. This layer is so warm because unlike the troposphere, where sitting in a room like the room you're in, there are trillions of molecules surrounding you. In the thermosphere, if I were to pump troposphere air out of your room and only pump in thermosphere air, there may be one air molecule in the entire room. So the air up there is extremely thin. Well, this air gets first crack at sunlight. So when sunlight is entering our atmosphere, you have these very few molecules that have access to this insane amount of sunlight. This causes the air there to become extremely hot. And in fact, it can become so hot, you can actually see what's called excitement. Basically, it starts to glow. And that can give you things like the aurora borealis. And this happens because sunlight is being absorbed by these molecules. They get really hot, they get really excited, they begin to glow. However, even though by definition it's the warmest layer of the atmosphere, those molecules are what are warm. Everything else, there's nothing to absorb sunlight. As a result, everything else would be cold. So even though by definition it's the warmest layer in the atmosphere, the air molecules in that layer are warm, but they're fewer and farther between. So if you went up into the thermosphere, you'd still feel cold. Ironically, if you've ever heard of the International Space Station, or if you've heard of many satellites, or if the space shuttle, believe it or not, many of those operations actually take place in the thermosphere. They do not go all the way into the exosphere. And so ironically, space shuttles, the International Space Station, even though they say they're in space, they're actually still in the Earth's atmosphere. They are not above the top of the atmosphere. That's crazy to think about. So the thermosphere is pretty thick, at least in terms of its height. It's a pretty thick layer, but there are very few air molecules in it. Everything above this layer is the exosphere. That's all I'm going to say about the exosphere. But yeah, the International Space Station is in the thermosphere. It orbits Earth from the thermosphere. The last thing I'm going to talk about when talking about these spheres of the Earth is there's another layer that spans the mesosphere and the thermosphere called the ionosphere. This is a layer of charged particles. Basically, when the sun is out and sunlight is hitting those rogue molecules higher up in the atmosphere, those molecules get excited. This causes them to suddenly shoot off electrons. And so this creates an area with a large electrical charge. And this takes place in the upper layers of the atmosphere. Now, I'm not going to pretend to be an expert on this, and I'd be the last person that I'd want to really talk a lot about this. But here is what happens. When you have a layer of these electrons, these excited electrons, it makes it hard for AM radio to spread far. It actually gets absorbed into this, ionosphere, and that causes it to diminish. During the daytime, AM radio waves can't travel very far. However, at night, there's no sunlight exciting these molecules. So there aren't as many free electrons, there aren't as many ions, there isn't nearly as much of that. As a result, the ionosphere is much thinner. And as a result, AM radio waves can travel very far. In fact, if you're in the right location, you can hear radio stations from thousands of miles away. There's actually a really cool video. I'll actually post it as a link into this video from a YouTube channel called Half as Interesting that talks a lot about AM radio waves and the ionosphere. It's really cool stuff. The last thing I'll talk about is temperature in the atmosphere. So if you notice, each one of these layers treated temperature differently. And we actually divide the atmosphere into these different layers based on these temperature changes. Temperature decreases with height in the troposphere and the mesosphere. Temperature increases with height in the stratosphere and the thermosphere. We'll go back to that figure that I showed at the beginning of this talk about layers, and you would notice that as you go up with height, temperature declines in the troposphere. It then levels off and begins to rise in the stratosphere. Then it levels off and begins to drop again in the mesosphere, and so on. You can easily identify where one layer ends and another begins by looking at these changes, where temperature stops decreasing, levels off, and starts increasing. However, as I warned you, be careful, and especially when you do this week's activity, be really careful when identifying where one layer ends and another begins, because inversions are common right near the surface of the Earth. So make sure you're able to tell the difference between a surface inversion and the tropopause. If you see an increase with temperature and height right near the surface of the Earth, that's a surface inversion. That's not the tropopause. The tropopause is going to be much higher. And then just to review, air pressure and air density decrease with height. The atmosphere is divided into different layers based on how temperature changes with height. In the troposphere, temperature decreases with height. In the stratosphere, it increases with height. In the mesosphere, it decreases with height. And in the thermosphere, it increases with height again. So you get this zigzag-like pattern. Well, that's it for now. The next thing I'm going to talk about is all of this information I've already talked about, the difference between weather and climate, all these things we know in the atmosphere. Well, how do scientists actually get this information? How do they get to these conclusions? Well, that's going to be talked about in the next lecture when we talk about the scientific method. Until then, thank you for watching.